right. Hi guys. Welcome back. I have not done a video for what is it? Like 3 weeks. So we're gonna do unit 7, chemical bonding. This is 60 questions. I'm gonna try my best to just do this in one go. I'm gonna try and go a little bit fast. So, you can just use the feature on YouTube where you can just like slow down the video. So if you feel like you need to do that, go on ahead. I'm just going to get right into it. Number one, we're given these three structures. Okay. We're given these Lewis dot structures. Okay. You can draw Lewis dot structures in a variety of ways. I normally draw them with little dashes. Okay. But you can draw them like this. This is in your guided notes. Pictures of Lewis dot structures drawn like this are available in your notes. Okay. The way that we would typically draw them would be like this. We would typically have sulfur. And hydrogens look like this. So instead of these two electrons being drawn like that, you can just replace it with a dash. Same for these. Those are the pairs of electrons that these atoms are sharing with each other. This can also be drawn like this with a double bond there, double bond there. And this here would be a single bond between the fluorines with all of the other, I'll draw it over here, 6 dots around each one. So you can draw them either way. But anyway, this question is asking which atom, when bonded as shown, has the same electron configuration as an atom of argon. Now, argon's configuration is 288. So really, one of the tricks that you can do is go and look at the periodic table, find the element that is the closest physically or by atomic number to argon, and that would be sulfur. Okay. Also, if you think about it, sulfur's configuration is 286, and look at what's happening to it. It is bonding with this hydrogen, and each one is not completely donating an electron, but sharing their electrons with sulfur. So sulfur is getting an electron shared, 1 electron from each hydrogen. So this really would be 2888. And so it would, once it's bonded to each hydrogen, have a configuration similar to argon. Number 2, which molecule is nonpolar and contains a nonpolar covalent bond? Okay, so if we look, we have CCl4, we've got HF, we've got HCl, and we've got F2. This one should really be the one that we just know off the bat is nonpolar, okay? The bond itself between F and F is nonpolar because they're the same element, okay? Electronegativity for fluorine is 4, so 4 minus 4 is 0. This falls into the nonpolar range. So again, as long as the bonds in between your atoms are nonpolar, then regardless of its shape, the whole thing will also be nonpolar. Okay. Number 3, let me get rid of all of this stuff. Okay, so number 3, they're giving us these 4 different diatomic molecules. Well, this one is not diatomic, but they're mostly diatomic molecules containing a triple covalent bond. So which one has a triple bond? So now that we know how to draw Lewis dot structures, we can figure this out. So H, right, if there's 2 of them, I know that each hydrogen has 1 valence electron. So this is going to be the pair that they share. So that's it. It's just a single bond. Okay. Now chlorine, I'm going to just draw that one over here. Chlorine is a halogen. So these all have 7. Okay. And right here, there is our 1 pair. Again, remember that these electrons over here, they're kind of like locked up and not available for bonding really. So the ones that are by themselves on a side are going to be the ones that are available for bonding. And between chlorine, we also have a single bond. So this is out. Okay. C, we don't even have to draw because it says diatomic. Okay. This is not diatomic. Di means 2. Atomic is atoms. So this does not have 2 atoms. It's got 3. So that's out. This, by the way, is ozone. That's what makes up the ozone layer. Okay. We're only left with choice D, but let's just take a look at what it looks like anyways. So nitrogen has 5 valence electrons, and 3 are available for bonding. So there is a pair. there's another bond, and these can also bond. I mean, we wouldn't really draw it like this. It really looks like this with a triple bond in between each other. So we would want to go with choice D. Number 4, which formula represents a nonpolar molecule containing polar covalent bonds? Let me just get rid of all this stuff too. Oh no, I forgot a drink. Oh, I need water. Gonna get thirsty. Oh boy. All right, whatever. Alrighty. So they're saying that the molecule itself has to have, like, the bonds between the atoms have to be polar covalent. So I know that automatically I can get rid of C because H and H, they're the same atom. So the difference in their electronegativities is 0. So this bond itself is nonpolar, regardless of the shape. All right, water. All right, so we've got O and we've got H. The electronegativity for O is 3.4, and for H it is 3.2. So this is a polar bond. No, 2.2. Sorry. So the difference is 1.2. So this is definitely a polar bond. Okay, so this is a contender. But the problem is that because of the shape of water, we have partial charges. All the charge is basically brought up, the negative charge is brought up towards the oxygen. This molecule is bent. It is asymmetrical. If something is asymmetrical, it means that overall it is polar. So A is out, and again, C is out. Let's look at D. This is ammonia and H3. Okay, the individual bonds, if you take the electronegativity differences, you will see that it falls into the polar range. And again, because of the shape, all of the charge ends up going basically to the top of the molecule towards nitrogen. So it's also asymmetrical. So this is an overall polar molecule. Carbon dioxide is one of the examples where you have individual polar bonds, right? The CO bond, carbon has an electronegativity of 2.6 and oxygen is 3.4. So when you subtract them, the difference is 0.8. So this does fall into the polar range. So this bond here and this bond here, those are polar bonds. However, oxygen is the more electronegative thing. So this oxygen tugs on carbon's electrons that way to the right, and this oxygen here will tug that way. There is no clear side where the electrons are going to more. And so we say that this molecule is overall nonpolar because it has even charge distribution. So we would want to go with choice B. All right, number 5. Okay, so this is really just memorizing properties of ionic and molecular or covalent compounds. So they're asking which terms describe a substance that has low melting point and is bad at conducting electricity. So you definitely wouldn't want to pick anything that says metallic because things that are metallic or that are metals are very good at conducting electricity. So those are out. Okay. Ionic compounds have very, very high melting points, not low melting points. So C also doesn't count. Anything that is covalent or molecular is going to have a very low melting point generally and is typically a pretty bad conductor of electricity. So we would want to go with choice D. All right. Back up to question 6. All right. Okay, the carbon atoms in a diamond are held together by, we're going to want to go with covalent bonds. So diamond is one of our network solids, okay? And everything in a diamond, all the atoms are carbon. They're all linked together in a network, so on and so forth, okay? But carbon is non-metal. So when non-metals get together, it is still considered a covalent bond, network solid or not. Number 7 is really odd. So N2O3, by the way, all these questions are from the region, okay? I just pulled them from regions. So N and O are both nonmetals, which would make this a covalent or molecular compound. Excuse me. Now, when we name molecular compounds, we don't use Roman numerals. Roman numerals are used for ionic compounds. Also, in the name for a molecular compound, you should see prefixes. So I'm going to say none of these. Okay. If I were asking you to name this, we should go with the format that we've normally gone with. We've got 2 nitrogens, so that would be dinitrogen. And we've got 3 oxygens. Remember that your second nonmetal has a name change for the ending. Oxygen turns into oxide. And since we have 3 of them, it is trioxide. So this should really be what it is called. Okay. Not really sure what's up with those choices, but all right. Next, number 8, which diagram best represents a polar molecule? So off the bat, I can eliminate A. Where's my pen? Okay, I can get rid of A and I can get rid of D, okay? H2 and Cl2, those are both diatomics. All the diatomics are nonpolar because you have 2 of the same element. The difference in their electronegativity is 0, which is the nonpolar range. Now it's between B and C. And this one is also kind of easy because Na is a metal, Cl is a nonmetal. This is not covalent at all. This is ionic, okay? The word polar is referring to polar covalent bonds. So ionic bonds we don't consider them to be polar, okay? So it's definitely not C. Polar is indicating that you have 2 elements that are both nonmetals. So our only choice would be choice B. And HCl, again, hydrochloric acid, as we've gone over many times. All right, number 9. Which compound has both ionic and covalent bonds? Now, something like this is going to be, you're going to see either a metal and some nonmetals, or you'll see polyatomics together, 2 polyatomics together, something like that. So let's look at our choices. So CO2, this one is not ionic at all. We've got 2 nonmetals, okay? Carbon dioxide looks like this, okay? There is nothing ionic about this. We don't have positive and negative charges here. Same for choice C, okay? This is an alcohol. We haven't done these sorts of compounds yet. That will actually be our next unit. These are all non-metals, and there are no charges involved here. So it's not A and it's not C. Okay. Let's look at choice D. Na and I. We've got a metal and we've got a non-metal. This is automatically ionic, but I don't see any other non-metals. There's only 1 metal and 1 non-metal. That means that there is only 1 type of bond, and that would be ionic. You have a positive sodium coming together with a negative iodide ion. The sodium is donating 1 of its electrons completely over to the iodine. Choice B is the only one that has both types of bonds, okay? So we have sodium, that's Na, and then we have this, we have CO3. This is carbonate. This is one of our polyatomic ions, okay? So here's our metal, okay? Our positive metal is associating with our negative polyatomic ion. This is specifically an anion, and it's polyatomic because this CO3, this is like a little chunk of elements, and overall it has a charge. But the way that these 2 elements are being bonded, the carbon and the oxygens, they're being bonded together through covalent bonds. They're all sharing their electrons with each other. So between sodium and carbonate, this whole thing, this whole cluster, that is ionic. But in this thing, in this polyatomic ion, polyatomic ions are held together through covalent bonds. So we would want to go with choice B. Alrighty. Number 10, which formula represents a tetrahedral molecule? So tetrahedral, I could draw it, not very good at this. Okay. This is one of the examples that I want you guys to just memorize, okay? So this one is going to be CH4. This is methane. Methane is one of our nonpolar nonpolar substances, okay? So CH really looks something kind of like this, and it's hard to draw. because it's really three-dimensional. It's not flat like this. It's not flat. Okay, it's really a tetrahedron. Okay, so it is 3D. If I were to draw it, oh, this is not going to work out well. This is not working out. Let me see if I could just Google it so we can get a better idea. Let me get rid of all this stuff. We can just get a better look at it. Okay. So we were looking at CH4. Nope, this is not working. Wait. Okay, CH4 molecular geometry. So we can take a look at what it actually looks like. All right. Here we go. So this is what it really looks like. This is a better drawing. Okay. So here is methane. Okay. So here is our carbon and here is our hydrogen. All of our hydrogens. Now, all of these hydrogens, the bond angle in between all of them is 109.5 between there and there, between this one and this one, this one and this one, this one and this one. All of the angles are exactly the same. So this whole molecule, it has an even charge distribution and it has symmetry, which is what makes this whole thing overall non-polar. But just know, because we didn't really get too much into the names of the shapes, but you should know that methane specifically has a tetrahedral shape. Okay, so we would want to go with, again, choice C for number 10. All right, number 11. Identify a type of strong intermolecular force that exists between water molecules, but does not exist between carbon dioxide molecules. So again, water, superpolar, carbon dioxide, nonpolar. Okay, so nonpolar molecules really are not held together very well. They have very weak intermolecular forces. That's why carbon dioxide likes to be in the gas phase, has very weak intermolecular forces. So it doesn't really have anything trying to keep the molecules together. All right, so I'm just going to draw them out. We've got CO2 and we've got H2O. Now, why would water have stronger intermolecular forces? Well, that's because water has something called hydrogen bonding. Hydrogen bonding is the strongest type of IMF or intermolecular force keeping molecules together. So you can say, you literally don't even have to explain, just identify. You can say hydrogen bonding. Okay, so water has hydrogen bonding. Meanwhile, carbon dioxide doesn't. You can also say that it has dipole attractions. Again, because water has a partial positive, partial negative charges, or you can say dipole forces. Any of these are fine. I personally would probably go with hydrogen bonding, but it is up to you. Anyways, number 12, atoms of which element can bond to each other to form chains, rings, and networks. Now, this one, you can sort of answer it at this point, but we would get more into this in Unit 8, where we talk about organic chemistry, which is all based on carbon, the compounds that carbon is made up, that make up carbon, bleh. All the compounds in an organic compound, I wish I could erase this, but I just do not have the time to edit these videos. All of organic compounds, what they all have in common is that they're all made up of carbon. There we go. I've got it. All right, so it is going to be A. All right, let me just give a quick explanation as to why. Carbon has 4 valence electrons, okay? And they're actually all available for bonding, okay, because they're not kind of like tied up in those little pairs. So carbon can just keep doing this. It can just form into really, really long chains and usually has hydrogens completely surrounding it. Again, we'll get more into this into the next unit, but just know at this point that carbon can form into chains, rings, and networks because it has 4 valence electrons available for bonding. Also, please, I'm sorry, excuse my absolute brain fart a moment ago. Anyways, moving on. Number 13. Okay, which is the formula of an ionic compound? Again, ionic compound, you've got positives, you've got negatives, you've got metals usually with nonmetals. So CO2, we should at this point be able to look at this one and know that it's not only covalent, but it's also nonpolar, okay? Not A. Carbon dioxide is a covalent compound. SO2, I've only got nonmetals going on, okay? Sulfur and oxygen, no charges are involved really here, so it's not B. Same thing for D, all nonmetals. If I look at C, I can see that I have Na plus and I have OH minus. Again, this is hydroxide ion. This is a polyatomic. And this is why I say not to memorize table E, but just be familiar with it. Things are a lot easier if you can just look at a compound and be like, oh, look, that's hydroxide. I know that that's a polyatomic ion being paired with a metal. So this is definitely the ionic compound. Okay, again, a lot easier if you're just familiar with the polyatomics. But anyways, number 14. Which terms represent two categories of compounds? This is really just definition sort of stuff. So the two categories of compounds that we've been going over would be not A, ionic and physical. That does not make sense. Ionic and molecular, bingo, that's the one. Again, another way that you can really call molecular is covalent. They're not exactly the same thing, but they are similar enough. Chemical and molecular don't make sense. Chemical and physical also don't make sense. Okay. Number 15. Oops, let me get rid of all this. All right, which set of procedures and observations indicates a chemical change? So remember that there are certain indicators that we're going to be looking for to show us or to demonstrate to us that a chemical change is occurring. Again, in the chemical change, a new substance is being formed. So choice a cool shiny metal is added to water in a beaker and rapid bubbling occurs. If you see bubbling, this is gas formation. This is a clear indicator of a chemical change. So we're going to want to go with A. If you look at the other ones, ethanol is added to an empty beaker and the ethanol eventually disappears. This is because it's evaporating. That's a physical change. C, large crystals are crushed with a mortar and pestle and become powder. So you're just changing the physical form, but it is still the same crystal. You haven't changed what it is. You just changed what it looks like. D, a solid is gently heated in a crucible and the solid slowly turns into a liquid. This is melting. Again, another physical change. So A is the only one that makes any sense. All right, number 16. Which atom in the ground state has a stable valence electron configuration? The only ones on the periodic table that are stable as is are the noble gases. So you just have to look for the noble gas, and that one is Ar, argon. Alrighty. Number 17, given the equation representing a reaction, so we see that we have diatomic chlorine, and it is being broken up into two molecules of chlorine, two atoms of chlorine, sorry. So they're asking what occurs during this reaction. Okay, so this is where you want to use barf. Remember barf, okay? Broken, absorbed, release, formed. So we can see that we're taking chlorine, diatomic chlorine, and we are breaking it up, okay? So we are breaking bonds here, and in order to break bonds, so breaking means you have to absorb energy. So energy is absorbed and a bond is broken. Choice A. Number 18, which statement correctly describes diamond and graphite, which are different forms of solid carbon? So when they say different forms, what these things really are, diamond and graphite, these are allotropes, okay? Allotropes are basically physical forms in which an element can exist. So there are three common allotropes for carbon. They're diamond, graphite, and also charcoal, okay? All of these substances are made completely of carbon. These are all network solids, okay? But the structures are all different, which is what gives diamond, graphite, and charcoal their different structures and all of their different properties and different appearances as well. Okay, so we're going to want to go with choice B. Because they differ in their structure, they also differ in their properties. Okay, another example that the regent loves to give is O2 versus O3. This is oxygen, this is diatomic oxygen, this is the stuff in the air that we like to breathe. And this is ozone. This is the stuff that makes up the ozone layer. Okay, there are two completely different things. They have different structures, and because of different structures, they have completely different properties as well. Alrighty, moving right along. I need some water. Okay, what type of bonding is found in the molecule HBr? So I can see that I don't have, it's not ionic, all right? So I've got H, I've got Br, okay? So it's not metallic. There's no metals there at all. It's not ionic. We know that this is going to be covalent. It's going to be either polar or it's going to be non-polar. So that's really what we need to narrow it down to. So what we got to do is we need to look up the electronegativities of each. Okay. So hydrogen has an electronegativity of 2.2 and bromine is 3.0. So highly electronegative. Now, because the difference falls, it's 0.8 is the difference, this falls in the polar range. Okay, and this molecule, the charge is going this way. It's being pulled completely to the right because bromine is more electronegative, has a stronger attraction for the electrons than hydrogen does. So this is not an even distribution of charge. So this one is going to be polar. All right, number 20. Which formula correctly represents the compound calcium hydroxide? Again, this is why it's good to know the polyatomics. Calcium, go find calcium on the periodic table. You will see that its charge is 2+. Go to table E, you will see that hydroxide is OH negative. Now we have to put this stuff together and figure out what the formula looks like. Again, this is going to be our crisscross method. So the 2, let me do a different color. This 2 right here tells me how many OHs I need. And this imaginary 1 right here tells me how many calciums I need. So I need 1 calcium. So I'll write Ca. We don't really put 1s as subscripts, they're just implied. And I need 2 OHs, but I cannot write it like this. Cannot do that. When you need more than one of a polyatomic ion, you have got to put it in parentheses. So the OH goes in parentheses, and then I put my 2 on the outside. So we're going to go with choice B. All right, 21. So we did a question already about methane, that's CH4. So which statement best explains why a CH4 molecule is nonpolar? C and H have the same electronegativity. They don't. They're close, but they're not the same. CH4 has a symmetrical charge distribution. This is the definition basically of what makes something nonpolar. The charge distribution is going to be equal or it's going to be symmetrical. So you definitely want to go with B. Okay. C, that has nothing to do with it. D, also not true because all covalent compounds are going to have nonmetals. But whether they're polar or nonpolar, it depends on multiple factors. Okay, electronegativity difference, charge distribution, shape of the molecule, so on and so forth. So B is our best answer. All right, 22. Explain in terms of electrons why the bonding in an NaCl is ionic. Guys, again, for short response, please don't go on and on and on. Sometimes when you keep going on and you keep saying more, you end up saying something wrong and it just completely undoes all the good stuff that you did right. So keep it short, keep it sweet. Okay, so all you really have to say is that Na donates or transfers, you can say either word, 1 valence electron to chlorine, and this is what makes it ionic. That is it. That is all you need to say. Okay. Number 23. A characteristic of ionic solids is that they, so this is from, I think the last lesson, 7.10. Okay. This is just properties and characteristics of ionic versus covalent compounds. So a characteristic of ionic solids is that they have very, very high melting points, and this is because the electrostatic attraction between them. Again, in something like NaCl, you have Na plus and Cl minus. So it is a full charge, a full positive charge here, a full negative charge here. It's not like a polar covalent bond where it's only partial charges that are keeping them attracted to each other, okay? In order to break apart these positive and negatives, it takes a lot of heat in order to be able to melt them. So they typically have really, really high melting points. Okie dokes. Number 24. Which molecule contains a nonpolar covalent bond? So they're not saying that the whole thing is nonpolar. They're asking if the individual bonds are nonpolar. So off the bat, we should be able to figure this one out without even going to table S. It should be B, okay? BR and BR, regardless of what the number actually is, it's the one number minus the same number. So the difference is going to be 0, and that falls in the nonpolar range. Again, all of our diatomics, Honkel-Brith, they're all nonpolar. Number 25. A solid sample of copper is an excellent conductor of electric current. Again, metals are really good conductors of electricity. Which type of chemical bonds are in the sample? Metallic bonds. Metallic bonds, present in metals. We have a mobile sea of electrons that allows electricity to be conducted. All right. Number 26. Which is the formula for sodium perchlorate? Perchlorate is one of our polyatomics. So that information is in table E. So sodium, that's Na plus, it's got a plus charge. Where do you find that? Go to the periodic table. ClO4, that is perchlorate with a negative charge. So we have to do the crisscross method, okay? But this one is simple because we only need one of each because a positive one and negative one already cancel. So overall, it's just going to be NaClO4. So we're going to want to go with choice B. All right, 27. Two atoms with an electronegativity difference of 0.4 form a bond that is 0.4 to about 1.69 is the polar covalent range. Okay, so it's definitely not ionic. It's definitely covalent. Okay, 0.4 or 0, just 0 to 1.69. That's nonpolar and that's polar. So that's all the covalent stuff. So it's definitely covalent. Covalent involves electrons that are being shared. So A does not make sense. Okay, if electrons are transferred, that's describing ionic. So we're going to want to go with choice C. Okay. Number 28. When a reaction occurs between atoms with ground state electron configurations 2,1 and 2,7, the predominant type of bond formed is, so let's actually just figure out what these elements are. 2,1, let's go to our periodic table over here. Oops, my bad. Okay, so 2,1, that is lithium right here. Oops, my bad. That's lithium, configuration 2,1. And 2,7 is gonna be right over here. That's fluorine. So Li, a metal, is getting together with a non-metal. Okay. Let's go back. Bear with me. So this is basically the definition of an ionic bond. Okay. Again, we've got lithium, positive charge, fluorine with a negative charge coming together to make lithium fluoride. This is ionic. Lithium is completely transferring its one valence electron over to fluorine so that both are satisfied, okay? Number 29. Given the electron dot diagram, we have HF. The electrons in the bond between hydrogen and fluorine are more strongly attracted to the atom of. So this is polar covalent, okay? There is an uneven charge distribution because hydrogen has electronegativity of 2.2. Fluorine is the most electronegative one on the table with electronegativity of 4. So there is a huge difference on where the electrons want to go. They're really, really, really being pulled towards the fluorine, okay? So our answer is going to be A. The electrons in the bond between hydrogen and fluorine are way more attracted to fluorine because it has a super high electronegativity. Alrighty, that's it for 29. Halfway through, 130. Okay. Which electron dot diagram represents H2? So again, you can draw the two dots like this, or you can just do like a dash. I prefer the dashes, but a lot of Regents questions are like this. So I'm just going to go ahead and draw H and H, and I know that each one has a valence electron. Okay, so they're going to share them like this. The other way that you can do it is instead of doing the dash, they're just sharing 2 electrons with each other. So we're going to want to go with A. Hydrogen has nowhere near this amount of electrons. That just does not make any sense. And this one also doesn't make sense because you don't share a single electron, you share a pair. They're always shared in pairs. So we're going to go with choice A. Number 31. What is the number of pairs of electrons shared in a molecule of N2? So each nitrogen, if you go to the periodic table, has 5 valence electrons. 3 are unpaired, so they're available for bonding. So let me just choose another color. So this one is available. Those can pair. These can form a bond, and these can also form a bond. We would never write it like this because it looks terrible, but we could rewrite it like this. There's a triple bond in between our nitrogen atoms. And so they're asking, what is the number of pairs of electron, not number of electrons total, but pairs. And again, each line represents a pair. So there are 3 pairs. That's a triple bond. Number 32, metallic bonding occurs between atoms of what? Well, metallic bonding happens in metals. So you just got to look for the only metal, and that would be copper. Alrighty, next page, going down to 33. All right, so the formulas and the boiling points at standard pressure for ethane, methane, methanol, and water are shown in the table below. So we are being asked to explain in terms of molecular polarity why the solubility of methanol in water is greater than the solubility of methane in water. I really actually, I don't know. I'm going to go over this one, but I really cover this more so in a different unit, unit 10, where we talk about solutions. But anyways, okay. So things that we say, we have this saying that like dissolves like. Okay. So this means that things that are polar mix really well with other things that are polar. Things that are polar and non-polar usually do not mix very well together. An example of this would be water. Water is very polar, and oil is non-polar. That's why water and oil just don't mix. Okay, they're not soluble in one another. This has to do with your molecular polarity. So they're saying, why is the solubility of methanol in water greater than the solubility of methane in water? That's because methanol right here is polar and methane is nonpolar. Okay, so what we can say is that methane, I'm going to rewrite this. Actually, you know what? I'm going to use this cool little feature. Look at this. Hold on while I erase. This makes my life easy. Okay, so methane is nonpolar while while methanol is polar. Water is also polar. So other polar substances will dissolve more easily in it. And done. That is a good explanation. Okay, I mentioned polarity. Okay, I spoke about solubility of methanol versus methane. Okay, so I have kind of like ticked off all of the boxes. All right. Okie dokes. Moving on. Nope, not what I want. Okay, number 34. Draw a Lewis electron dot diagram for a molecule of hydrogen fluoride. So, okay, gonna draw my, where's the marker? Where'd it go? So I've got H, got 1 valence electron. Fluorine is a halogen. It's in group 17. It's got 7. Each one has 1 electron available for bonding. So here is our Lewis dot structure. I'm just going to neaten it up a little bit, get rid of those little dots, and it should just really be just 1 dash. This is a single bond between them. Okay, and this is our Lewis dot structure or Lewis dot diagram. All right, number 35. Which change is most likely to occur when a molecule of H2 and a molecule of I2 collide with proper orientation and sufficient energy? So we've got H2 and it's combining with I2. So what's going to happen when these two things come together? We've actually seen this chemical equation before. What's going to happen is they're first going to break up into H and I, and everyone is separate, and they're going to reform. This H is going to get together with this I, form HI. It's a new compound. And this one is going to bond with this one. So we're going to really get two of these things. Okay. This is a chemical change. Okay. We've made new substances. So it's definitely not A and it's not C. A chemical change because an element is formed. We did not form an element. We formed a compound. So we're going to want to go with choice D. Number 36. The name of the compound KClO2 is potassium. Again, know your polyatomics. ClO2 is chlorite. This is potassium chlorite. ClO2, find it on table E. That is chlorite. Number 37. Which formula represents a substance that contains covalent bonds? A, not it. That's ionic. That's lithium, a metal with chlorine, a nonmetal. Same for C. Calcium is a metal. Chlorine is a nonmetal. That's also ionic. Same for D. Potassium is a metal and oxygen is a nonmetal. That is also ionic. The only thing that is covalent here is choice B. Carbon dioxide specifically is nonpolar covalent. Alrighty. Number 38. Base your answer to the following, yada, yada, yada. They give us all this information. And then at the end of the day, they just ask us to identify the polarity of an HI bond and the polarity of an SS bond, okay? SS is easy, okay? SS bond is nonpolar. The difference in electronegativity, I don't even need to look it up. The difference is 0, okay? We do, however, need to look up the values for H and I, okay? For H, it is 2.2, and for iodine, it's 2.7. This still falls into the polar range, okay? So the HI bond is polar. And again, sulfur, I believe it's 2.6. So 2.6 minus 2.6 is 0, although it doesn't even matter what it is because it's the same element. The difference is always going to be 0. So the HI bond is polar and the SS bond is nonpolar. That's it. That's sufficient. All right, number 39. Let's get rid of all this. Down. Okay. Which substance can be decomposed by a chemical change? The only thing that can be decomposed by a chemical change is a compound. So you just have to look for the thing that is not an element. Argon, element, that's a noble gas. Sodium, that's one of our metals. It's in group 1. Sulfur, group 16, that's one of our other nonmetals. Ammonia, this one, again, we should know that's NH3. NH3 is a compound that can be broken up into nitrogen and 3 hydrogens. So we want to go with ammonia. 40. A hard substance that has a high melting point and is a poor conductor of electricity in the solid phase. Okay, this is describing ionic compounds. Ionic compounds have very high melting points, but they don't conduct electricity very well when they are in the solid phase, right? So this would be our answer, table salt, NaCl, sodium chloride. This is the only thing here that is ionic, okay? Solid table salt doesn't conduct electricity well. You would have to put it into water, okay? Conducts electricity better in the liquid phase. Number 41. Which formula represents a molecular solid? So molecular, basically another way to say covalent. So A doesn't make sense. That's ionic. B doesn't make sense. That is not molecular at all. It's literally just one metal. So that's not it. D, NaCl, that's sodium chloride. That's ionic. No. This is sugar, okay? Sugar is a molecular compound and it's also a solid. So we're going to want to go with C. We see all nonmetals. Alrighty. Number 42. Which electron dot diagram represents a molecule that has a polar covalent bond? Don't let the dots trip you up, Okay. This one is, we can do a lot here just because of process of elimination, actually. Li, you see a plus sign and you see brackets. If you see brackets in a Lewis dot structure or electron dot diagram, it means it is ionic. So get rid of A and get rid of D. Those are both ionic. Okay. They're also asking for polar covalent. Cl and Cl, that is nonpolar. All of our diatomics are nonpolar. The difference in their electronegativity is 0. The only thing that is polar covalent would be HCl, with the negative charge going more towards the chlorine because it has a higher electronegativity. Number 43. Which compound contains only ionic bonds? Okay, so A is not good. Although this is an overall ionic compound because we have ammonium, NH4 plus, this is one of our polyatomics, coming together with negative chlorine, right? So we have this whole positive and this whole negative coming together. That is what makes this ionic. However, it's not just ionic bonds that exist here, okay? This is an ionic bond between these two things, between the cation and the anion. But within this cation, what's holding together the nitrogen and hydrogen is a molecular or covalent bond, okay? It's not A. B, that's all nonmetals as well. Again, same kind of spiel as A. D is going to be our final answer. We have a metal, we have sodium, and we have oxygen. So we have a metal and a nonmetal coming together, transferring our electrons from sodium to the oxygen. C, definitely not. We should know off the bat that water is a polar covalent molecule, not C. Alrighty. I keep saying that like a pirate. Okay. Anyways, 44. Which statement describes the energy and bonding changes as 2 atoms of fluorine become a molecule of fluorine? So I'm going to draw this out. So they're saying 2 atoms of fluorine. That's F. Oh no. Oh no. Where did it go? Here it is. There we go. Voila. We've got 2 atoms of fluorine, one here, separated by this little beautiful plus sign, and they become a molecule of fluorine. So we're forming diatomic fluorine. This is another example of barf. So start barfing, okay? Don't start barfing, please. I don't want you to be sick. Okay. Anyways, barf. Broken, absorbed, released, forming. Okay. So what are we doing? We are forming a bond between 2 fluorine atoms and they're becoming one molecule. Okay. So we are forming, that's F, and that's paired with R. So in order to form a bond, you need to release energy. So it's definitely not A and definitely not D. Okay. So again, energy is released as a bond is formed. So choice B is the one that we want to go with. Alrighty. Number 45. Let me get rid of all this nonsense all over the place. Okie dokes. Number 45. What is the total number of electrons shared between the atoms represented in this formula? So they're not asking about pairs, they are asking about total number of electrons. Now remember, each dash represents a pair. In a pair, you have 2. So these oxygens are sharing 4 electrons with each other in total. Answer is 4. All right. Number 46. Hydrogen forms a negative ion when it combines with sodium to form NaH. So we end up with something that basically looks like this. Okay, Na plus, H minus. Okay, and this happens primarily because hydrogen has a greater attraction for electrons than sodium has. Sodium is a metal with very low electronegativity, so it really kind of like can't wait to get rid of its electrons, and hydrogen really wants another one because it wants to fulfill its outer shell. It wants a full outer shell. Okay, so sodium gives away its 1 electron to hydrogen, and again, hydrogen wants that electron because it has a much greater attraction for electrons, higher electronegativity than sodium does. Okay. Moving on, number 47. So they're asking us to draw a Lewis electron dot diagram for a molecule of HCl. So this is really similar to the other one we did. We've got H, 1 valence electron, chlorine, another halogen with 7. We've only got these electrons available for bonding. So this is literally our Lewis dot structure. I'll draw it here a little bit nicer. And this is our final answer. Okay, that's our Lewis dot structure. And number 48, explain in terms of charge distribution why a molecule of carbon tetrachloride is a nonpolar molecule. I actually don't even need to know what this thing looks like, okay? Because they're telling me that it is nonpolar. If something is nonpolar, it means it automatically has even charge distribution. So I'm just going to write CCl4. You can write out carbon tetrachloride, but you guys should know what the formula is because you know how to name stuff. CCl4 has an even charge distribution. And this is what makes it nonpolar. Distribution. Okay, my spelling. All right, I think that's spelled correctly. Yes, that is the same as that. Good. Okay. So carbon tetrachloride, or CCl4, has an even charge distribution, and this, again, is what makes it nonpolar. All right, number 49. Explain in terms of, they give us all this information, and then they ask us to explain in terms of intermolecular forces. They're saying in terms of, so make sure that the word intermolecular forces is in your answer. Explain in terms of IMF why tetrachloroethene has a higher boiling point than tetrachloromethane. So tetrachloroethene has a much higher boiling point. Things that have higher boiling points, it has a higher boiling point because the forces that are keeping those molecules together are very strong. Means that it takes a lot of heat in order to break them up and get them to boil and turn into the gas phase. So things that have higher boiling points, higher melting points, typically have stronger intermolecular forces. So we can just say that tetrachloroethene has stronger. I'm just going to abbreviate right now, but you should write out intermolecular forces in full, okay? Then tetrachloromethane. That is a very long word, okay? So again, this one has a higher boiling point because the IMFs are much stronger than this one over here. All right. Okay. All right. So number 50, we've got 10 more. Beautiful. All righty. So which process represents a chemical change? This is sort of like going back a few units. Chemical change, again, new stuff is formed, evaporation, physical change, melting, physical change, crystallization, physical change. Okay. So the only thing that we're left with is corrosion. Okay. Corrosion, decomposition, all those things are all chemical changes. So that would be choice B. All right. 51. The high electrical conductivity of metals is primarily due to, this is because of its mobile electrons. When you have mobile electrons, this is what allows a substance to be able to conduct electricity. All right. Number 52, almost done. An element with an electronegativity of 0.9 bonds with an element with an electronegativity of 3.1. Which phrase best describes the bond between these elements? So 0.9 and 3.1, if you subtract them, the difference in their electronegativities is 2.2. This is way higher than 1.7, which means that this is ionic. Also, something with an electronegativity of 0.9 is probably a metal, and something with electronegativity 3.1 is probably a nonmetal. So that's also what would clue you in to this being ionic. So we would want to go with mostly ionic in character. So get rid of A, get rid of D. Ionic in character and formed between two nonmetals. That's not what ionic is. Ionic is typically between a metal and a nonmetal. So we want to go with choice C. Okay, 53. Given the equation representing a reaction, we've actually had this question. This was one of our questions for this lesson. I think this was the very first lesson that we did for the unit 7.1, I think. So we're given this equation. We already looked at this equation before, by the way. Which statement describes the energy changes that occur in this reaction? So a few things actually have to happen. I'm going to draw this out. So we start off with H2 diatomic hydrogen, and we also start off with I2. Okay, so these are two different things. They're both diatomics. And what has to happen is these first have to break apart. So this has to break apart into just I and just I. So then now they're separate. And this has to break apart into H and H, two separate things. So in order to, again, this is barf, okay? So in order to break apart stuff, so broken means you're absorbing, okay? So you have to first absorb energy to break bonds, okay? Then we have to reassemble this stuff to make this, okay? So now this will bond with this, that will come together, and this H will come with this iodine. And we will end up with something that looks like this. Overall, you end up with these two molecules, new molecules. They're not the same substance at all. So this is a chemical change. Okay, we end up with something like this. So again, we first had to break the bonds here between these diatomics. And in order to break them, you had to absorb energy. So that's right here. Energy is absorbed as bonds are broken. But then you need to re-put them basically together, reconfigure them into a different arrangement. We took this H and we combined it with this iodine. So in order to form new bonds, you have to release energy. So energy is released as bonds are formed. So two things really have to happen in order for this whole thing to work out. So we want to go with choice D. All right. 54. A substance was found to be a soft, non-conducting solid at room temperature. The substance is most likely what? Again, this is just knowing the properties of ionic versus molecular. This is describing a molecular solid. No, wait, where's the orange? I like the orange. Okay. So this is again describing a molecular solid. Okay. Okie dokes. 55. All right. So which structural formula represents a polar molecule? Again, there are four that I asked you guys to memorize. Okay. So one of these should just be really easy. You should just be able to spot it. It's this. It's H2O. H2O is one of the most important polar molecules that we talk about. Okay. All right. So 56, moving back up. Okay. In the formula for the compound, X Cl4, X is not an atom, it's just representing something. What could the X be representing? So we've got 4 chlorines. I'm going to draw this out. We've got chlorine, this one, chlorine, another one, and I'll just do the other one over here. So we've got 4 chlorines, and they all have available 1 electron here to bond with. So this means that we need 1 atom that can attach to all of these things. So we need to have something that has the ability to bond or have 4 different bonds, and that would be carbon. Carbon has 4 valence electrons like this, and all 4 of them are available for bonding. All right. So 57, which substance is a conductor of electricity in the liquid phase, but not in the solid phase? I already said this one before. This one is NaCl. Table salts or all other ionic compounds, they're very, very good conductors of electricity when they have been dissolved in water. So when they're in the liquid phase, but not when they're in the solid phase, okay? Number 58, which of the following chemical bonds is the most polar? So we're going to have to go to the periodic table, table S, and find all of the electronegativities of these elements, subtract them, and figure out where it falls in our range. So I'm just going to, you guys can do it on your own, but I'm just going to give you the differences, okay? So for the first one, for A, the difference between TE and H is 0. Sorry, I got to get the pen back. The difference here is 0.1. For OH, it is 1.2. For SH, it is 0.4, and same for the last one as well. Now, 0.1 is really, really nonpolar, okay? And 0.4 is right at the beginning of being polar. So an SH bond is polar, but not really polar. It's like very slightly polar. And same thing for SE and H. So OH, you can see here, it is the most polar thing here. This falls sort of on the higher end of our polar range, okay? All right, so number 59, we've only got 2 more questions. Which element would most likely form an ionic bond with chlorine? Chlorine is a nonmetal. So what would form a bond with a nonmetal in order to make an ionic compound? That would be the metal. So just find the metal, and that is going to be potassium. Okay, potassium is in group 1, will form KCl, potassium chloride. Oops. Last question. So we are given this table with 4 different solids, A, B, C, and D, and then we're giving some of their properties, melting point, conductivity in the solid state, and then also their solubility in water, okay? So they're asking us which one could represent diamond, okay? Diamond is completely made of carbon, okay? And it is a network solid. So it is molecular, all right? So this is something that is molecular or covalent. So knowing the properties of molecular covalent compounds versus ionic is what is going to help you here. Okay, so diamond has a very high melting point. Okay, network solids, or this one in particular, very high melting point. So we're not going to want to go with choice D. Okay, diamond does not conduct electricity well in the solid state. Molecular compounds usually don't conduct electricity well. So we're not going to want to go with choice B. Okay, so it's pretty much in between A and C right now. So now the final thing is looking at the solubility in water. If you take a diamond and you put it in water, does it start to dissolve? No, it's not soluble in water. So that one also doesn't make sense. So we would want to go with C. So diamond has a high melting point, very hard to melt a diamond, does not conduct electricity well, and it also does not dissolve in water. So we're going to go with choice C. All right, you guys. So that is it. Let's see how we did on time. I think that was about an hour or so. So yeah, again, I really hope that this video is helpful to you. Again, if I went too fast, you can always pause it. Write stuff down, you can slow it down. Also, what I would really recommend is, I should have said this at the beginning of the video, but whatever, for the future videos, I guess, I would do them myself and then I would check my answers after, okay? Or do them as you go. Try a question, press play, watch for the solution, so on and so forth. But anyways, again, hope this was helpful. Best of luck on the exam, and I will see you guys in the next video.